tell you a little bit more about trace and determinant, where they come from, one way to think about them, and how that connects with the diagrammatic language that I use sometimes. Okay. So a couple of definitions that I've already made, but those V and W are finite dimensional vector spaces. I said that one way of writing the space of linear transformations from W, now let's change these, V and W, from V to W. One notation people use is this one, V star tensor W. And you'll recall that V star is the space of linear transformations from V to the field, V dual, the dual vector space. Okay. So that means that, by taking double duals, I've also defined implicitly, V tensor W is the space L from V star to W. So in this graphical notation, I write an arrow like that to represent a vector space. Right? And there's like a linear transformation sometimes associated to it. But right now, I just want to talk about the arrow itself, which represents the vector space. And it turns out to write a tensor product like this, you just write V tensor W. You just write them right next to each other. So this represents the vector space V tensor W. The dual space associated to a vector space, V star, is somehow a very special arrow, right? It's a very special vector space. So I could write, here's V and here's V star, but that makes invisible the special relationship between V and V star. So we'd rather pick a notation that somehow allows me to connect them. And so here's the notation that works. I just write V, and then I put an arrow going in the opposite direction. Okay. So when we were talking about how V and V star are isomorphic, but V and V double star, V double dual, are canonically isomorphic. The reason they're canonically isomorphic is because there's this map, which you could think of as like an evaluate map, which takes an element alpha in V star and an element V in V and spits out alpha of V. Right? That was how I created an isomorphism from V to V star star, which is equal to the space of linear transformations from V star to F. And that is the vector V maps to alpha gets sent to alpha of V. That's this idea of evaluation. So evaluate eats a V star and a V, and it spits out an alpha of V, a field element. So what does that tell you? Tells you that in this graphical notation, that is how I write V star. That is how I write V. Evaluate, whatever it is, let's just call it EV, associated to some vector space V, has to map V star, V down to the field. So this is V star tensor V by this first definition here. And that gets sent to the field, so it's got to be some box here, right? Because by the field, we wrote just the blank board. So it's some box here. This is this map F. Turns out there's a very happy choice for that, which is that I can just draw it like this by connecting these two. That's part of why, essentially why it makes sense to choose the arrow going in the opposite direction. So this says, this is the map EV, evaluate, that eats something in V star, something in V, and spits out a field element. It's exactly this map over here. There's another map, which is kind of the transpose of this, which goes in the opposite direction. It goes F to V, V star. And you could think about that as being like, well, you take an element and a field element, and you just multiply it by the identity matrix, and then you sort of reshape the identity matrix in the right way so that it's a vector instead of a covector, or instead of a linear functional. And this is kind of the reflection of this. So it has also, it goes from the vector space to V, tensor V star. So it has a picture that looks like that. And there's a related one where I swap it up and down. So I can make it go like that also. But you can think about it as being, I just do this. But okay. So there's another transformation that's kind of the other half of these. When I combine those, so if I have a linear transformation, a linear operator that goes from a vector space to itself, and I attach to it this map and the flip version of this map, it's just doing that, making a little loop. This loop, because this evaluate map I could define without picking any basis for V, the value of this loop shouldn't depend on the basis that I've chosen. So this should be somehow a basis-independent quantity that depends on F. And what it is the trace. It's the trace of F. Now, what other quantities could I construct without making any choice? Well, the only other thing I can really do using these elements is to repeat F. Right? So I can do something like this. F, F. And this would be the trace of F squared, or the trace, i.e. the trace of F composed with F, which is going to be a different number than this in general. And the point is that all these invariants, all these things like trace and determinant, can be constructed by combinations of such pictures. Let me give you an example. So suppose I have just 2 by 2 matrices. And I might as well assume that I've chosen a nice basis so that they're upper triangular. So I have lambda 1, 0, lambda 2, and something I don't care about. Let's call it A. Right, so that's my F, or properly my F in some basis. MB of F. Okay, so the trace of F is equal to the sum of the eigenvalues. And the determinant of F is equal to the product of the eigenvalues. And I'd like to get those two things entirely from pictures like this that don't depend on these maps that don't depend on the basis. Right? Well, okay. The trace of F, this guy, is lambda 1 plus lambda 2. And the other thing I can do is I can have 2 F's and compose them first. What's that going to be? Well, if I square this matrix, I get lambda 1 squared, lambda 2 squared, 0, and something I don't care about, right? This times that, lambda 1 squared, that is lambda 0, lambda 2 squared. Okay. So this one is going to be, the trace of that is lambda 1 squared plus lambda 2 squared. So in order to get out the determinant, in the case of a 2 by 2 matrix, I have to square this. So if I do F times itself, I get lambda 1 plus lambda 2 squared is lambda 1 squared plus 2 lambda 1 lambda 2 plus lambda 2 squared. And then I just subtract this, I'll subtract off this part, and I'll get the stuff in the middle by itself. So determinant of F in this notation would be 1/2 2 loops, loop times loop minus the composition. So just warning, this is special to the 2x2 case. So in order to get the determinant for, say, a 3x3 case, I'm going to get a more complicated expression because I have more terms to get rid of. Okay. And as a last sort of bonus property for this, we'll prove later on that the hard way that if I have 3 linear transformations and I take their trace, or any number of linear transformations, I'm allowed to cyclically permute these. So this is equal to the trace of GHF is equal to, I can't do any permutation, but I can cyclically permute it, HFG. It's not equal, for example, to the trace of HGF, but I'm allowed to cyclically permute them. And in this notation, what we're saying is that if I have a loop, I'm allowed to take these guys and slide them around the loop, and that doesn't change the value. So like that's FGH and that's GFF. So any way of permuting those, and these two things are equal. That's all we're saying. Okay. So this part is just, so I don't expect you to, I'm not going to test you on these pictures. I'm telling you this because it's how I think about them, and I think it's helpful to kind of get an idea of where these otherwise somewhat mysterious things come from. Because they're in a sense the only things you can possibly say without choosing a basis by using these canonical maps, evaluation and co-evaluation.